Engineering Department, NIT Trichy. And I am showing my gratitude to the organizer for giving me this wonderful opportunity. And this is my PhD research, which I have done under the supervision of Dr. Rohit Becker, sir, Electrical Engineering Department, MNIT Jaipur. And a RAM product designed for enhancing power system flexibility. And if you are looking at the number of slides, it is 109, but don't worry, working slide is only 45. Remaining are added to address your in-depth queries. And these are the key areas where I am going to focus on. We are witnessing ever increasing energy demand. To meet that, the renewable penetration in the power system across the globe is increasing. And also, we need to achieve the carbon emission targets. Fossil fuel-based generation results a huge carbon emission, so we have to reduce it. So renewable penetration is increasing across the globe. However, this renewable generation is highly uncertain and variable. And these two terms, it again leads to discussion of more than 1 hour. And uncertainty means predictability. It is not 100% predictable. And another thing, variability, means from time to time it is varying. So the main challenge is it is uncertain variability. So we don't know how much variation will be there, but it is continuously varying. And this uncertain variability is creating different challenges such as frequent system imbalances, renewable energy curtailments, negative prices, and extreme market price volatility. To overcome these challenges, we have to enhance power system flexibility. Power system flexibility is the ability of power system to offer counter fluctuation to renewable generation variations or load generation variations. Power industries are using different approaches to enhance power system flexibility, such as energy storage. Here, battery energy storage or pumped hydro plants are using, but huge investment is required in this. And another is fast response resources. The resources such as gas power plant, diesel power plants comes under this. And also here also huge capital investment is required. Another is improved grid infrastructure. Tie-line interconnection with the different power systems. Here also huge investment is required. Another is demand response. Here we need fast communicating devices because there should be proper communication between system operator and the end consumer. So here also huge investment is required. And another is improved operations. Here modified unit commitment or economic dispatch or accurate forecast, all those things are comes under this. And here it uses the existing infrastructure. So it offers a least cost solution. And I have already told if you want to accommodate more renewables, we have to enhance power system flexibility. And this figure justifies that statement. And this shows California generation profile of California in 2022. And here 4 curves are there, load is there, wind generation is there, solar generation is there, and net load is there. Net load is the difference between total load and total renewable generation. And our conventional generators should be scheduled for this net load. And also the flexibility requirement estimation, it should be based on net load. And if you are seeing at this figure, you can observe that at multiple time points, system need ramping up and down. Actually, this figure is plotted in hourly basis. If you are going for minute ways, every minute system need ramping up and down requirement. So we can tell that if you are enhancing ramping capacity, system flexibility will automatically enhance. So we need to enhance ramping capacity. In other words, if we are telling if insufficient ramping capability or availability shortages can lead to system imbalances, and I am stressing on ramping availability because ramping capability most of the time it will be there, but the generating companies are not ready to provide their ramping capacity to the system because they are not getting any specific monetary benefit to do that. And if they want to provide ramping capacity, they have to change their generator output from maximum efficient point, and also rapid up and down ramping and increase the machine maintenance. So to overcome these challenges, mature power market, they have introduced a special ancillary markets called FRP markets, where the generating companies can bid their ramping capacity and they can maximize their profit because FRP price is higher than energy price. So they can achieve more profit from FRP markets. This enhances the ramping availability in the system, which help to accommodate more renewables. And there are 2 products, ramp up product and ramp down product. And it offers the least cost solution because there is no specific infrastructure requirement, and also both system and GenCos are get benefited. So this results quantum research attention for FRPs. And FRPs are integrated into real-time economic dispatch. Mainly two type of real-time economic dispatch strategies are available. One is single interval and another is multi-interval. In single interval, we are producing next interval dispatch instruction. In multi-interval, we will produce advisory dispatch instructions along with next interval dispatch instruction. And this advisory dispatch instruction will help system operator to prepare his generation in advance. So multi-interval strategy is better than single interval. Even though FRP got quantum research attention, there are challenges which have to be addressed. One is RAM product design necessitated accurate net load forecast. In current literature, there is only little attention towards net load forecasting, and more focus is given to load and renewable generation forecasting. And mainly two type of net load forecasting techniques are available: direct and aggregated. And we have to find which is most suitable for RAM product design. And obviously, the model which produce accurate net load forecast, which will be suitable for FRP design. And to address renewable variations all over the world, real-time economic planning timeframes are reduced from a day ahead to 5 minutes ahead. So we need very short-term net load forecast. And another is existing RAM product designs are mainly focused on wind integration, because these FRP markets are introduced in US or European scenario. Their wind integration is more than solar integration. But the countries like India, we are having more solar integration, and we are planned around 175 gigawatt by 2022, and out of that 100 gigawatt from solar generation. So we have to focus such systems also. For very short time frame, solar is more variable than wind. So large solar penetration necessitates huge up and down ramping requirement, and also especially during morning and evening hours. And traditional FRP designs considers only end-time uncertainty. End-time uncertainty-based FRP design can result ramping shortages, because solar is having high uncertain variability during morning and evening hours. And also existing FRP design use approximate uncertainty modeling. And we need multi-interval real-time economic dispatch compatible FRP designs. And all conventional units are not eligible to participate in FRP markets, and the modern conventional units have high ramping cost. And also, if again we are using conventional units, conventional fossil fuel units to support renewable generation, we can't obtain the expected environmental advantages. And because of this, recent studies focus on renewable RAM product, but such studies are mainly focused on wind generation. And there is little attention towards ramping availability from other renewable sources such as solar. And solar is having inherent ramping characteristics, especially during morning and evening hours, that can be used as FRP. Considering these challenges, this research is having mainly for objectives direct net load forecasting, aggregated net load forecasting, and it proposes a conventional flexible RAM product and a solar flexible RAM product. And first objective is direct net load forecasting. In conventional power system, load was only uncertain variable, and system operational planning were based on the load forecast. But in modern power system, multiple uncertain variables are there, such as load or renewable generation, specifically wind and solar. So handling multiple uncertain variables in operational planning is difficult or complex. So to avoid that, we have to compile these multiple uncertain variable into a single variable that is called net load. Net load is the total load minus total renewable generation. Our conventional generators are scheduled for this net load, and also the ramping requirement estimation needs accurate net load forecast. And this is the proposed direct net load forecasting model, and it works based on the gray system theory. Information systems are classified into three: black system, white system, and gray system. In black system, no information is known. In white system, all information is known. In gray system, partial information is known. In gray system theory, it models the system using the available data. Here also we are having the historical data. Based on that, I have modeled a system using first order differential equations. Using that model, we are obtaining direct net load forecast. And the proposed model is having three steps. In first step, it estimate net load time series, and second step, it obtains net load forecast using gray index models. Here we can see three models are there: GM11, GM12, and GM13. Here the first one shows it is represented by first order differential equation. Second one shows how many variables are used in each model. In GM11 only one variable is used. It is a univariate model. Previous time step data is used here. In GM12, previous time step plus previous year similar data is used. In GM13, previous time step plus two previous year similar data is used. And in last step, it obtains forecasting performance parameters and also compare forecasting performance with standard model like ANN. And for analysis, 5-minute load, wind, and solar generation data from BPA balancing area is selected, and seasonal analysis is conducted to understand the performance throughout the year. And also, different intervals from morning, noon, evening, and night are selected to understand the performance throughout the day also. So figure 4 shows the performance of the proposed models in winter season, and figure 5 shows performance in transition season, and 6 shows summer season. We can observe that in all season, proposed GM13 model outperforms all other models. And if we are observing the transition season, we can see that the median line, it will be a little higher than these GM12 and ANN model. However, the 75% of data, this is up to this is 75% of error, that is closer to 0. So it is producing much better result than other models. And table 1 shows the annual performance of different models, and we can observe that proposed DGM13 model outperforms other models, and also ANN is better than DGM11 and DGM12. And afterwards, to ensure the optimal model performance, residual correlation is estimated using autocorrelation function, and figure 7 shows autocorrelation function plot. And we can observe that there is no particular pattern exist in the ACF plot. That means no information left in the residues to improve the model performance. And if you are summarizing first objective, and if you are observing here, you can see that MAP maximum is 5.54. Means almost all these models are showing accuracy above 94%. That is, it is highly accurate because it includes the uncertain variables such as load and wind. And addition of previous year similar data help to improve the accuracy that we can observe from DGM11 to DGM12 and DGM12 to DGM13. Forecasting performance is improving here. And seasonal analysis show that summer season is having least error. If you are observing these figures, summer season is having least error because in summer season climate is more stable, less uncertainty is there. And still we have obtained a 94% accuracy, but still we can improve this accuracy further. We can use aggregated net load forecasting for that. That is done in the next objective. Here aggregated net load forecasting. In in objective 1 we have done direct net load forecasting. There we have used the historical net load time series to obtain net load forecast. Actually, net load is a combination of multiple uncertain variables like load, wind, and solar generation, and each variable is how different dependent factor. So exogenous factor selection for forecasting is very difficult there. In aggregated net load forecasting, we are obtaining net load forecast by the aggregation of individual load, wind, and solar generation forecast, and their expected forecasting errors also used. And several established methods are available for finding exogenous factors for these load, wind, and solar generation forecasts. Therefore, aggregated net load forecasting can produce accurate results compared to direct net load forecasting. And figure 8 shows proposed aggregated net load forecasting model. It uses modified gray index models, and gray index model in the objective 1 is modified by adding correlation based feature selection, and it also uses Gumbel Copula for net load uncertainty estimation. Proposed model is having 3 stages. In first stage, it obtains individual load, wind, and solar generation forecasting. In second stage, it obtains net load uncertainty using Gumbel Copula based JPD of load, wind, and solar generation forecasting arrays. In third stage, it obtains preliminary net load forecast. After that, it upgrades preliminary forecast with estimated net load uncertainty. Finally, it obtains a central point, that is a final aggregated net load forecast. And here the positive and negative net load uncertainty is estimated using the left and right side of NLF error distribution. This NLF error distribution is estimated or modeled from JPD samples of load, wind, and solar generation forecasting error. NLF error distribution is shown in equation 1. And these JPD samples are evaluated using Gumbel Copula. And here I have used Copula theory and specifically Scala's theorem. Scala's theorem states that JPD can be estimated from a given Copula function and given marginal distributions. And several Copula functions were available like Gaussian Copula, Frank Copula, T Copula. And several studies on such Copulas shows that Gumbel Copula is suitable or it is having best performance because Gumbel Copula is suitable for modeling the dependence between extreme events. And such extreme events are important in power system operation planning. So I have used Gumbel Copula here. And upward net load uncertainty is estimated by taking the standard deviation of right part of is a distribution, and negative uncertainty is calculated by taking the standard deviation of left part of is a distribution. And net load up forecast means we are obtaining interval forecast. So there will be an up forecast and down forecast. So up forecast is obtained using equation 4. And down forecast is obtained using equation 5, and final central forecast is obtained using equation 6. And Gumbel Copula is modeled using the historical data, and JPD is simulated in SAS on demand for academic software. And figure 9 shows the box plot of joint distribution, and it shows a load forecasting error distribution as well as a wind and solar forecasting error distribution. And figure 10 shows the estimated net load error distribution. And figure 11 compares proposed model with different models. Here, support vector regression model is used for comparison. In objective 1, ANN model is used here. Support vector regression model is used because in recent studies show that support vector regression is showing superior performance over ANN models. So here, the proposed model performance is compared with support vector regression model. And from the figure 11, we can clearly observe that the proposed AGM13 model outperforms all other models. And figure 12 compares the best model, AGM13 model, with preliminary forecast and actual values. We can observe that the proposed model forecast closely follow the actual values compared to preliminary net load forecasting. And here the best model performance is optimal model performance is ensured using residual correlation calculation. And two kind of residuals are calculated using ACF and PACF, partial autocorrelation function. And figure 13 and 14 shows ACF plot and PACF plot. And here also we can observe that there is a particular pattern exists in the residues. So there is no information left behind the data to improve the model performance. So here if we are summarizing the objective 2, modified gray index models are used here, and it necessitates only a low quantum of training data, and it is having ultra fast operation because it uses momentum transfer behavior. And exogenous factor is selected using correlation analysis, and preliminary forecast is enhanced with net load uncertainty integration. And here, along with the final aggregated net load forecast, interval forecasts are also obtained. And proposed GM13 model outperforms all other models. And the net load forecast obtained from the best model can be used for FRP design in the next objectives. So objective 3, it proposes a multi-interval conventional RAM product. It considers both start and end time uncertainty compared to existing end time uncertainty based FRP. I will discuss that with the help of the figures. And if we are considering both start and end time, it can cover ramping shortages due to underestimated uncertainty because it covers wide range of uncertainty between start and end time. So proposed FRP modeling uses Gumbel Copula for net load uncertainty estimation. Gumbel Copula is suitable for considering extreme dependence between load, wind, and solar generation forecasting errors. The superposition of such extreme forecasting error can lead to system imbalances. So if we are considering Gumbel Copula based net load, if we are estimating Gumbel Copula based net load uncertainty, so we will consider all the extreme condition in the net load uncertainty. So it avoids system imbalances in extreme conditions. And proposed FRP design consider very short-term variation in utility level solar PV generation, and which is absent in the existing study because existing studies were focusing on wind penetration. And this is a proposed conventional FRP framework. It is having two stages: pre-dispatch process and co-optimization. In pre-dispatch process, we will estimate net load variability and uncertainty using load, wind, and solar generation forecast and their expected forecasting arrays. And afterwards, we will estimate FRP requirement using estimated net load variability and uncertainty. And in optimization, first we will optimize the conventional FRP cost, then we will clear FRP in multi-interval RTED along with energy and other ancillary services. And this figure shows the existing FRP design. T0 to T is one interval and T to T+1 is another interval. You can observe that here it considers only n time uncertainty. Here T0 was start point and T is a end point, but they consider only n time uncertainty. But all these data points are forecast only. So uncertainty can present at all time steps. So we have to consider both start and end time uncertainty. So this figure is the proposed FRP. Here both start and end time uncertainty is considered. If you are considering T2, T+1, uncertainty here as well as here also considered. And equation 9 and 10 gives the modified FRP design. And multi-interval RTED. In multi-interval RTED aims to minimize the generation cost and capacity cost correspond to regulation, spinning reserve, and conventional ramping cost. And it is simple economic dispatch problem. System studies are conducted on a small fiber system and a 260-bus practical system. And fiber system is given in this figure. And 3 case studies are selected for analysis. And first is wind penetration, where the generator G5 is replaced with a wind plant of capacity 400. And second is solar penetration, where G5 is replaced with a solar plant of capacity 400 megawatt. And third case was both wind and solar penetration, where G5 and G4 are replaced with a wind and solar plant of capacity 400 megawatt. And figure 19 and 20 shows morning FRD and evening FRD requirements of the test system. And 3 cases are shown. And here we can observe that the case 2, where the solar penetrations were there, it is having high FRD requirement during morning hours and high FRU requirements during evening hours. That means along with the normal ramping up of solar generation, it demands more FRP requirements. And cost of dispatch with without FRP, with end time uncertainty based FRP, with start and end time uncertainty based FRP, with Gaussian Copula based FRP, and Gumbel Copula based FRP. It is shown in table 2, and it is evaluated for all the intervals in a day, and for different cases also. We can observe that here dispatch cost, it is reduced in the proposed Gumbel Copula based FRP, and dispatch cost is reduced due to reduced imbalance penalties, because in Gumbel Copula based FRP we have considered all the extreme conditions, so there is less chance of imbalances in such case. And here in table 3 shows the cost savings with RTD without FRP. So here also we can observe that the proposed Gumbel Copula based FRP is showing more cost savings. And practical system BPA balancing area is selected, and it is having 25 thermal generators and 41 hydro plants and wind generation of installed capacity 4850 megawatt, and 400 megawatt solar plant is integrated into the system to simulate solar utility level solar plant penetration. And figure 21 and 22 shows morning FRD requirements and evening FRD requirements in different seasons. And here we can see that significant FRP requirement is there both in morning and evening. And also we can observe that transition season is having high FRP requirement, because transition season is having high uncertain climate. So the uncertainty part in the FRP is higher there. And similar to the test system, here also RTED is conducted for different FRP conditions, and we can observe that proposed Gumbel Copula based FRP is offering least cost solution. Here also cost is reduced due to reduced imbalance penalty. And this shows the practical system cost savings. The proposed Gumbel Copula based FRP is offering more cost savings. And here it shows both test system and practical system correlation of FRP and FRP requirements and cost savings. We can observe that in test system, the correlation is 0.86, and in practical system correlation is around 0.7. So high correlation exists between FRP requirements and cost savings. It shows that proposed design is suitable for system having high FRP requirements. And if you are summarizing the objective 3, and the proposed conventional FRP effectively manages the net load uncertain variability due to the increased renewable generation, and also it offers significant cost savings due to reduced imbalance penalty. And solar penetration results high FRD and FRE requirement during morning and evening intervals due to natural solar ramping. And seasonal analysis show that transition season need high FRP requirements due to high uncertainty. And the strong correlation between FRP requirement and cost savings show the suitability of proposed FRP in a very high renewable generator system. And in this objective, I have considered only conventional generator for FRP. So this can be extended to renewable generators. So in objective 4, it proposes a solar flexible RAM product. And conventionally, FRP availability from conventional and wind generating units are investigated. If you are using conventional fossil fuel generators to support renewable generation, it reduces the environmental advantages. And also lower time frame of FRP market and uncertain wind RAM availability weakens that such conventional and wind RAM products. And this demands wider investigation for RAM availability from alternate renewable sources such as solar generation, and coherency in system up and down RAM requirements with solar generation allow solar power plants to participate in FRP markets. The objective for proposes a solar flexible RAM product for wind penetrated systems and systems having very high daytime industrial load. And such SFRP is capable to meet forecasted ramping needs.
Please turn off your mic. Afzal Hamid.
Hello?
Yeah.
Okay. Okay. And also the proposed SFRP design consider both start and end time uncertainty compared to end time uncertainty based renewable FRPs. And the figure 25 shows the proposed SFRP design, and it is also having 2 stages, pre-dispatch process and co-optimization. In pre-dispatch process, 2 steps are there. It estimate the FRP system level FRP requirements, and also it estimate SFRP availability estimation. System level FRP requirement is estimated using net load variability and uncertainty, and SFRP availability is estimated using solar power forecast and expected forecasting arrays. And in co-optimization, 3 steps are there: FRP cost minimization, conventional FRP cost minimization, and SPPs profit maximization, and multi-interval RTED. So this is the proposed SFRP design. Here also, compared to the existing renewable RAM product, here both start and end type uncertainty is considered. So this is the proposed SFRP design. Again, RTD is the similar cost minimization. It aims to minimize generation cost, capacity cost correspond to regulation, spinning reserve, and conventional ramping and renewable ramping cost. And here also case studies are conducted on same 5-bus and 260-bus system. And load, wind, and solar generation forecasts are obtained by Gray Index models. And solar flexible RAM product availability is estimated using solar power forecast and estimated uncertainty. These solar forecast uncertainty and variability is used for SFRP estimation. So here the 5-bus system details is shown. Test system generator characteristics are shown in table 6. And a wind plant of capacity 400 megawatt installed capacity is added to the 5-bus system for creating a generalized wind penetration scenario. And also a SPP of capacity 400 megawatt is also added as a SFRP provider. And this table shows the RTED cost of different dispatches, and different uncertainty levels are considered here. FRP sigma correspond to FRP with estimated net load uncertainty, and FRP 1.5 sigma correspond to 1.5 times the estimated net load uncertainty, and FRP 2 sigma correspond to 2 times the estimated net load uncertainty. Because in real time, the uncertainty can vary. We don't know how much uncertainty level will be there. So different uncertainty levels are considered. and RTED is obtained for different cases such as without SFRP, NSFRP, and SFRP with end time uncertainty, SFRP with start and end time uncertainty, Gaussian Copula based SFRP, and Gumbel Copula based SFRP. We can observe that the proposed Gumbel Copula based SFRP offer least cost solution. Here the dispatch cost is reduced due to two reasons. One is low cost ramping availability from solar generation reduces the dispatch of conventional generators for ramping. And second is reduced imbalance penalty, because now more sources are available for ramping. So obviously more ramping availability will be there. It will reduce the system imbalances and imbalance penalty. And figure 27 shows the credits and profits of SPPs. Actually, here the credit is credit due to energy market participation is evaluated. Hello.
Yes, sir.
Okay. Here two variables are considered: SPP FRP and SPP EP. SPP FRP is a credit that is obtained due to FRP market participation, and SPP EP is a credit that could obtain due to energy market participation, and the profit or additional revenue is estimated as the difference between these two variables, and we can observe that significant cost saving is there. Because FRP cost is FRP price is higher than energy price, so SPPs are obtaining a significant additional revenue or profit due to FRP market participation. And again, same BPA balancing area is selected, and it is having 25 thermal, 41 hydro, and wind generation of installed capacity 4850 megawatt. To simulate the generalized global generation mix of dominant thermal generation, the net interchange is deducted from the hydro generation. So the proposed the considered system is having more thermal generation. And figure 28 shows FRU, FRD availability, and as well as SFRU, FRU, FRD requirements, and SFRU, SFRD availability. From the figure, we can observe that transition season is having high FRU and FRD requirements, and also morning and evening have high SFRU and SFRD availability. And this table shows the dispatch cost of practical system. And here also similar to the test system, proposed Gumbel Copula SFRP is offering least cost solution due to two reasons. It avoids or reduces the dispatch of costly conventional unit, because the ramping availability from solar generator is less costlier than ramping availability from some conventional generators. And second is imbalance penalty is reduced due to the increased ramping availability in the system. And this also shows the credits and profits of practical system. And here also we can observe that significant profits or additional revenue can obtain by the SPPs due to FRP market participation, because FRP price is higher than energy price. So they can participate in FRP markets rather than participating in energy markets. So this figure 30 shows the correlation between FRP requirements and SPP's profit, and the high correlation exists between SPP's profit and FRP requirements. And this shows the business opportunity for SPPs, because solar power providers can participate in FRP markets so that they can obtain more profits. If summarizing the objective for case studies, both case studies are showing both system and solar power providers are benefited in the proposed framework. SPPs are benefited by increased profit because selling price of FRP is higher than energy price. System is get benefited by increased RAM providence. Means more number of FRP sources are available. This reduces system imbalances and imbalance penalty. So it reduces total dispatch cost. And strong correlation between FRP requirements and SPP's profits show that SPPs can participate in systems having high FRP requirements. And concluding the total research, the proposed research gives a least cost solution for increasing power system flexibility by modifying system operations such as real-time economic dispatch. And enhanced flexibility will help modern power system to accommodate more renewable generation. And two forecasting models are proposed, and accurate forecast obtained is used for the FRP designs, and two FRP designs are proposed, a conventional FRP design and renewable FRP design, using accurate net load forecast and estimate net load uncertainty. And proposed conventional FRP design effectively manages uncertain net load, variability of net load, and also it offers significant cost savings. And proposed solar flexible RAM product is beneficial to both system operator as well as SPPs for reducing dispatch cost and increasing profit margin respectively. And solar RAM product also offer significant environmental advantages because it reduces conventional generators dispatch for ramping. And every research, it opens a lot of future opportunities. Here also I have found a lot of future opportunities are there for further research, and I have listed only few. One first objective, direct error forecasting can be again improved by adding a DSP based data filtering technique such as Kalman filter to avoid input data outliers. And also we can use advanced machine learning algorithms to improve direct error forecasting accuracy. And aggregated data forecasting accuracy can be improved by using some probabilistic forecasting techniques such as Markov chain Monte Carlo technique, or we can use some advanced net load uncertainty estimation techniques. FRP design accuracy also can be improved by adding some advanced uncertainty estimation technique. And we can propose, here I have used the co-optimization. Instead of that, we can propose a bi-level optimization, and strategic bidding framework can be used for FRP clearing, which will help to improve the market clearing efficiency. Also, pricing framework for FRP can be proposed. And another thing here, the dispatched FRP, it will reach to system through transmission lines. Here transmission lines constraints are not considered, so we have to consider that for ensuring the reliability. And also unplanned outages, we have to consider that also. So we can add transmission line reliability and security constraints. And proposed conventional FRP can be incorporated in advanced optimization, stochastic optimization process such as stochastic economic dispatch and stochastic unit commitment. And also we can investigate more ramping availability from other renewable sources such as tidal and wave energy, which will again increase the benefit of renewable energy, and also system will get benefited by increased number of flexibility providers. And the proposed SFRP reliability can be enhanced by adding reliability and transmission line constraints. And here tri-level optimization and strategic bidding framework can be used for SFRP clearing to improve market efficiency. And these are the publication from the research, and these were the key references. Okay, thank you.
Okay. Thank you so much, sir, for this enlightening and research-oriented presentation. Now we will have a QA session. If anyone has a query, please feel free to ask here. You can post the question on the chat.
Yeah, I have seen one question, Tanuj Rawat.
Yes, sir.
Yeah, you have quantified flexibility using RAM product. Are there any other parameters which measure flexibility? Actually, I need to redefine the question because I haven't quantified flexibility with RAM products, because RAM product is used to enhance flexibility. It is not a quantification, and flexibility requirement is quantified with FRP requirement estimation. So FRP requirement estimation can be treated as a flexibility quantification. And other parameters, okay, here I have considered generation flexibility. Other parameters such as inter-area operation means how much power can be fastly transferred from one area system to another area system, that can be considered as a flexibility measure. I think I have answered his question.
Any other questions?
Yeah, actually, next question also from Tanuj Rawat only. In objective 3 and 4, in problem formulation, you have considered spinning reserve cost also. You are considering ramping cost which address uncertainty. Then what is the need of spinning reserve cost, because it also taken for uncertainty purpose? Actually, here the objective is to reduce the spinning reserve. If I am introducing a separate market, FRP market, my objective is to reduce the spinning reserve. if I can effectively dispatch the ramping, I can automatically reduce the spinning reserve. But in the proposed study, I have considered spinning reserve also because the FRP in FRP design also uncertain party is there. So to handle that uncertainty only, I have considered spinning reserve. Usually, the 1 or 3% of load is considered as spinning reserve. Here, the 1% of RAM product uncertainty is considered as spinning reserve. So it is different. It will address the uncertainty in FRP uncertainty. I think I have answered his question.
Yeah, actually he replied.
Yes.
Any other question? I think we're not having any other question. Uh, Now, on the behalf of TechCube Third and IEEE Student Branch MNIT, I would like to thank Dr. Sreenu for his valuable time and an insightful presentation. I would like to thank
Thank you.
all participants. Also, if you have any query, you can talk to directly speaker. His email ID is given in the poster I have shared. Thank you so much, sir.
Thank you.
Thank you.